I'm Colin Walls, and I'm here once again to talk about embedded software. Today, I want to talk about something that sounds depressing. I'm going to talk about failure. What I mean is failure of an embedded system. I want to consider what can go wrong and what we might do about it. Well, we all want to build reliable systems, and the fact is that the more complex systems get, the more likely failure can occur, the more likely unreliability can creep into the design. Now, what can we do about this? Well, the first thing is to recognise that failure can happen. Just admit it to yourself that something can go wrong. That's your first step. So don't expect to achieve perfection. Having accepted that, we then need to stand back and consider how we can detect failure, how we can mitigate failures, and the first point in that is identifying what they might be. Well, what can go wrong with an embedded system? Well, the answer is, everything really. The CPU could fail. Ain't a whole lot we can do about that actually. Once the CPU's failed, it's failed. So put that to one side. The software could fail. That's a big area to consider, and there's all kinds of defensive programming we can do to reduce the possibility of that. Peripheral devices can fail. That's something which can be considered very carefully. Memory can fail. Now, that's one worth focusing on some more. Memory in devices is now quite extensive. There's a lot of memory in most modern devices. And because of that, we have to consider very carefully what will happen in the event of failure. Now, it's not, to me, surprising that failure can occur. As I said, there's so much memory. The surprising thing is that failure doesn't occur more often. For example, a random bit swapping from 1 to 0 does occur quite commonly actually. And has your computer ever just crashed randomly for no obvious reason? Well, it may be because there's a fault in something, but it could be that one bit of memory flipped from 1 to 0 or 0 to 1 because of a passing radiation, a subatomic particle, and that bit happened to be somewhere in your computer that was being used at that time, and it caused something to go wrong. But it's very little we can do about that. We certainly can't protect ourselves against it. However, there are other kinds of memory failure which we can do things about. If there is a memory addressing failure, so the electronics that decides which memory words to use, if that goes wrong, well, we're scuppered. We can't do much about that at all. But other common sources of failure are things like stuck bits and crosstalk between bits. In other words, a bit can be stuck at 1 and 0 and not be changeable. Or crosstalk is when you write data to one bit and one or more other bits gets affected by that process. These can be detected and we can do something about them. The failure is most likely to occur on power up. So that's the time when we ought to do a bit of testing. And a test that we can do for that is called a moving ones test. The algorithm looks something like this. And basically the principle is we go through memory, setting each bit in turn and making sure that no other bits have been set. And making sure that it got set correctly, of course. This can only be done at power up simply because it corrupts all of memory. And it also takes a while, but it's worth considering doing. You can do a moving zeros test, which is the same principle. This code needs to be carefully written such that it doesn't use any memory itself. It doesn't use any RAM itself. It must only use registers for storing data. That's kind of obvious, isn't it? The other alternative is, having done that test at startup, is to run some more code during execution of our application to keep an eye on memory. Now, we can't corrupt all of memory, of course, but we could do some background testing. And we can use a test like this. This goes through each byte of memory and checks it out for stuck bits and crosstalk within the byte, or the word as the case may be. You could do it on words or bytes. And we only do one word at a time, one byte at a time. We turn off interrupts during that so that it doesn't matter that it's corrupted for a very small period of time. And that can be done as a background task, and it can detect a failure and perhaps reset the system or do something which will restore the status of that memory. Exactly what you do when a failure has occurred is an interesting subject. In general, you would want the software to put the system into a safe state and advise the user, whatever that means. That's another subject in itself. So that's it for today. Sorry, it's been a potentially depressing subject, the idea of failure, but I think one that we need to face up to, and I hope this gives you some guidance in the specific context of dealing with memory failure. So with that, I'll say bye for now.